So question 8's quite a lot of recall and applying information that you've remembered to the diagram you can see. It's on section 1.5 of the syllabus, the waves section, which is when you did that in year 9, so you might find you need to go back and look just at learning the facts from this part of the syllabus. So the first thing we've got here is the electromagnetic spectrum, and the first 3 parts ask us to name some specific parts of the spectrum. So name part of the spectrum with a longer wavelength than microwaves. Well, you have to remember which end of the spectrum is which. And there are 3 important things to remember here. That's energy, frequency, and wavelength. So the radio wave end of the spectrum, which in this case is on the right-hand side, is long wavelength, low frequency, and low energy. And the gamma ray part of the spectrum on the left-hand side is short wavelength, high energy, high frequency. They could draw this diagram either way around, so you can't just remember left and right. You have to remember that radio waves are the long wavelength, low energy, low frequency, and gamma rays are high frequency, short wavelength, high energy. So a longer wavelength than microwaves. Well, we find microwaves on the diagram. We go to the long wavelength end. The only option is radio waves, as it says on the mark scheme over here. Greater energy than X-rays. Well, again, we find X-rays, and we said the high energy end is the gamma ray end, so the only thing with more energy than X-rays is going to be gamma rays. Note over here it says accept this little symbol. It's like a Y. That's the gamma symbol. So you could accept the symbol, but since you've got gamma rays written in the spectrum, you should probably write that down. And then finally, a higher frequency than ultraviolet. Well, ultraviolet's here, just to the left of the middle, and we have 2 options here. Either X-rays or gamma rays would be at the higher frequency end, so either is fine. Okay, so then we move on to the properties of the waves that we can measure. So 8b, the properties of water waves can be measured easily in a school lab. The diagram shows information about the waves. So whenever you've got a diagram like this, the very first thing you look at is what's on the axes. And we've got wave height in centimetres and the distance away from the source of the waves, also in centimetres, on the x-axis. So how many complete waves are shown in the diagram? Well, a complete wave goes up and down and below the axis and back again. So there are 1, 2 complete waves in that diagram, because you can see an up part and a down part makes 1 complete wave. So that's 2. The wavelength of the wave, we have to remember the wavelength, the easiest way to do the wavelength is the distance from one peak to the next peak. And if you look, the first peak happens at 1 centimetre, and the second peak happens at a distance of 5 centimetres. So 5 minus the 1 gives us 4 centimetres. It's dangerous to try and do it from the middle, because if you go from the point where the wave meets the x-axis, the horizontal axis here, we go from 0 to 2, but that's only half the wave, it's not the full wave. If we want to do the full wave, it's all the way from 0 up to 4. So the easiest way to do it is peak to peak, or from the bottom of the wave here to the next part where the wave is at the bottom. These are called troughs. So trough to trough you could do as well, and that would be from 3 centimetres up to 7 centimetres, which again gives us 4. So that's the wavelength. Now, amplitude of the wave. The big mistake people make here is that they try and do the full height of the wave, and that's not what you need. You need the distance from the centre line here. That's where the water would be if there was no wave at all. So along that 0 line, just lying flat. You need the distance from there to the tallest part, to the peak again. And this time we care about the distance in the vertical direction, the y direction, the wave height. So the maximum there is 3 centimetres. Okay, and it doesn't matter, you see here in the mark scheme it says ignore plus or minus. Well, that's because you could say it's plus 3 centimetres or minus 3 centimetres, doesn't really matter. The 3 is the important part there. And then finally you have to remember the difference between longitudinal and transverse waves. Here it says the oscillation of the waves in the diagram, so that's the direction that the water's actually moving in, which is up and down, are perpendicular to the direction of energy transfer. So the energy is being transferred along the surface of the water. You get a wave where there's perpendicular in the description, that will be a transverse wave. Okay, so all you need to do really to remember that is the word perpendicular in this description is going to give us a wave that is transverse if we're talking about the energy transfer and the vibrations or oscillations. The other type of wave you could have is one where the energy transfer is in the same direction as the oscillation, and that wave is a longitudinal wave.